Good morning, everyone. This is Hitesh Shrimali from School of Engineering and Applied Science, and we are going to talk about digital logic using hardware descriptive language. This is CSE 213, and this is lecture number 1. Let's start with the course structure. It is divided into two parts. One is lecture and one is laboratory. In lectures, we are going to have various topics like number system. So, number systems like how to convert one radix system to another one. Majorly, like we are interested in binary, octal, and hex. However, binary is the most popular one, and later on we will realize that we need other two systems also, and we will work on it as well. And later on, we are going to study Boolean algebra. That's specifically for digital system where you are dealing with logic of ones and zeros. So when it's logic 1, it's on, and when it's logic 0, it's off. It's very simple. Or something is present, it's considered as logic 1, not present, it's logic 0. Something like that, we are going to use it in a binary system, and we might have various more system. Just for your information, let's assume that there is a system a0, A1, A2, A3. So this is a number in any system. So each one of them is known as a digit. Let's say if there is a number called 7329, then each one of them are known as digit in decimal system. Each one of them are digit. However, if you want to represent that, which is with, let's say, binary system where each one of them is represented with either 0 or 1, then each one of them is known as bit, and the combination of 8 8 bits are equal to byte, right? And 4 bits is equal to nibble, and you might have word also. So 16 bits of word, or maybe double word, and many other things might have there. So you can use them, and these will be the representation in binary. Okay, so you are going to deal with that, and you are going to make a Boolean algebra which is going to give you some function, or the function which is compact one, and that's the representing the whole digital logic, right? So with some combination that is going to happen. Let's assume that what I mean to say is as follows. Let's assume that there are two things. If this is a room where we are going to start a presentation, or let's say a lecture, when all students are here, all students, and of course the professor is here. So it's and logic of two things, all students and professor. So let's assume that all students, let's call them A, and professor, let's call this B. So the lecture is the output that will only happen when A and B both are present. So both are one, and then lecture will happen, or lecture can start. So this is one logic, and this was equivalent function. So I am talking about this function, and many more complications are there in terms of uh, OR gate, XOR gate, NAND, NOR, and many other gates are there, using which you are going to represent the whole function. And there might not be the unique solution. Sometimes you might have multiple answers, multiple way of representing that, and that will be taught in Boolean algebra. That's the second chapter, and all the simplification of logic functions using various methods like K-map and many other are there. We can use that, and we learn that. At the first, we are going to study the combinational logic. It does not use the system which is clock. Now, the system is clock means, I mean to say that clock is a technical word for digital. It's a heartbeat of your digital circuit or processor or whatever you want to design in terms of hardware, it is running at that frequency. If I am saying that I'm running at, let's say, 1 gigahertz, clock is 1 gigahertz means, by the way, this square wave has two levels, one is 0 and another one is logic 1. So 0 and 1, 0 is equal to low logic and 1 is equal to high logic. Note that this is not 0 volt and 1 volt. It is depending on the circuit and the logic. Sometimes this 1 might be equal to 5 volt, sometimes 1 might be equal to 3.3 volt, or sometimes 1 volt, 1.2 volt, depending on the technology which you are using. However, this 1 gigahertz means it's 1 nanosecond, right? The period is 1 nanosecond. That is the meaning of that. And the whole circuitry work at that frequency. And such kind of circuits which are running at time interval, or it's with some sampling, then it's going to be known as sequential circuits. In-depth study of sequential circuits in asynchronous, synchronous will be taught separately on chapter number 5. However, if there is no clock in the system and it's made up of only with logic gates, then it's a combinational circuit. However, if you are using a flip-flop or many other things which requires timing or running at the clock, which is most of the time the situation is like resistors, counters, flip-flops, maybe FIFO, LIFO, first in, first out, last in, like all these systems are there which you can use it. The next is the finite state machine, which is going to be useful to derive or to synthesize your digital circuit. So there are two phenomena are there, or two words. One is analysis and one is synthesis. What is analysis? Analysis means digital circuit or digital circuit is given to you and you have to find out, you have to analyze it, and using that you have to find out the final function using Boolean algebra or whatever way you want to find out. So that is analysis. In synthesis, you know the function, but you need to find out the digital circuit. Let's assume the case for, let's say you want to design a digital circuit which is behind the elevator system, where there are various floors are there, even some switches are there which are outside the lift, and how many number of floors are there. So you can use it, you can design it, or you can synthesize that circuit using finite state machine. So this is one way to synthesize it. Of course, when you have the FSM, you can write a code, right? And that code we are writing in HDL, hardware descriptive language, either in Verilog or in VHDL. You can also write register transfer logic, which is function is given to you, and you write the HDL code, and it will be in Verilog or VHDL. And this is also, FSM is also kind of behavioral modeling only. So you write the behavioral code or behavioral model of HDL and you write it in Verilog or VHDL, and you synthesize the circuit. So this Verilog is going to synthesize the circuit, and that will be burned in FPGA board before you are finally sending this for the chip fabrication process, right? So before making that, you are doing this. This is a bit different from Arduino board. Arduino board are also programming. However, it's actually inside inside hardware or inside inside Arduino, things are fixed, right? as many number of pins are there. So those are fixed, and you are writing a code inside this. You are burning it. You are connecting with input and output. It's like a microcontroller, or it's a microcontroller. So anciently we are using it from long back. However, this FPGA is all about the the board which has a chip. So I'm just drawing these pins. I don't know the exact number. It must be somewhere like 64 or maybe 48. So depending on FPGA board which you are using. So do not looking into the count of these pin numbers, right? So in this FPGA, there are billions of gates are there. Billions of gates, flip flops, and many other things are available inside this FPGA chip, which is in certain technology, by the way. For the current technology, maybe like 28 nanometer, 65 nanometer. That's the transistor size inside this FPGA chip. So there are billions of gates and flip flops are there. So which gates and which flip flop has to be selected for your given a function or given finite state machine or your behavioral model, that will be done through some various algorithms of flow plan, placement, and routing. So those things will be used. It's a separate understanding of such things. So we are not going into detail right now. However, when we are going to study same thing in the laboratory, we are going to in depth. We are going to learn it, and we are going to study that, right? And we are going to burn your code. So this is what we are going to study in the lectures. So you can expect these things, and we are going to study some sort of memory also, right? So that's the whole course structure. We are going to study this in given uh, given time of one semester. But in addition to that, we are going to have the laboratory session also. So various experiments are there, which we are going to do it with hardware descriptive language. Commonly, we are going to call it as a HDL, right? So we are going to model it, test some of the digital circuits. We are going to make SOP implementation of gate level and many other things like half adder, full adder. At the end, our aim is to make an efficient processing circuit which is dealing with arithmetic logics, right? So that's why we need half adder, full adder, subtractor, decoder, many other things other than encoder, priority encoder, comparator, all these things with timing means with clock, without clock. With clock is the combinational logic. With clock it's a sequential circuits. Whereas without clock and without flip flops, it becomes with 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 logic gates, it becomes combinational circuits, right? Without timing and clock, right? So this is what we are going to do it, and in addition to that, I'm expecting you to make one project. So after mid-semester exam, you select one project in a group of 4 and you submit it, and we will have the presentation as well. So this is our grading strategy. We are going to have mid-sem and end-sem both. I would like to have it open book. And we will have the assignments. Those are 4 in numbers. Total is 20%, and uh, this 20% assignments, we are going to have the exam. So I'm going to give you assignment well in advance, means 7 or 10 days before, and we are going to have the exam after that in the next week, so that that will be evaluated properly. Then you might have some surprise quizzes just to know that how I am teaching, because if you are able to answer those things, then there is no problem. So this is for my check also, and of course just to make sure that you attend every class, and it has weightage of 10%. Will And the rest of the things are on laboratory side, where you are going to have the project presentation, project report, right? And you have to write it down only in LaTeX. I'm going to share one 2-column IEEE format, in which you can write down the LaTeX report, and those report all the experiments which you are doing. So those reports are also expected to be written in LaTeX. Let's understand one more thing, that plagiarism has to be less than 15%, otherwise straight away F grade will be awarded, right? So let's agree upon that. I'm not going to reduce the quality, right? So this is the bare minimum thing which I'm expecting from you people. Do not copy, okay? Do not copy from anywhere actually, and get the report of less than 15%, then and then you should submit it, okay? Now let's start the course. The reference which I am following, it's Digital Design with an Introduction to the Verilog HTML. So I'm using this book. So the sixth edition is also available. You can use that. Even fourth is also available. So, but maybe third and fourth might not have Verilog HTML. However, this fifth and sixth has have HTML coding, right? So you can use that by Maurice Mann and Siliti, right? So the first topic or the first chapter of the course is number system. It has various topics. Whatever you are seeing in my slides, actually it's all originated from this book, right? Or some things have been taken from here also. So these are from there only. Let's start from the first thing. Let's assume that there is a number system 7392. How you are writing exactly is each one of the digit. So these are the digit. Each one of the digit has its digit value. Means this is unit. This is 10, right? Then hundreds, then thousands, so on and so forth. So you have to multiply that with the appropriate number which is given to you. So if you do that, you will get the 7392. This is actually true for all system where this particular thing, whatever I am multiplying, is known as the radix, or you can also say that the base of the system, right? But note that if it is 10, you have 10 numbers are there, which is starting from 0, so 0 to 9. So total is 10 numbers. That's why it's written with 10 in base, right? If I'm writing here, let's say, okay, one more thing is written over here, that to distinguish between number of different bases, basis is about radix, we enclose the coefficients in parenthesis and write a subscript equal to the base used. I mean to say, if I want to indicate that whatever is inside this box is actually a decimal, I'm going to write down 10 over here. If it is written 3, then it's base 3. But understand, in this case, you are going to have numbers ranging from 0 to 2 only inside this box. This for just a sanity check. You will not ever get any number which is 3, right, or 4, because that's not allowed in the base which is 3. But if it is a binary system with 2, you are going to have 0 to 1. It's only possibility of having two numbers, 0 and 1. If it is 8, there is a possibility going from 0 to 7. If it is hexadecimal 16, there is a possibility to go from 0 to, right? So now this is little bit different than what you studied. 0, 5, 6, 7, 8, 9. So till 9 there is no problem. But 10 is A, 11 is B, 12 is C, 13 is D, 14 is E, and 15 is F. So you can see over here, you can go from 0 to F, right? And when you are representing these numbers and you want to convert any of the base system to a decimal, you have to follow this equation. This equation is actually, these are the digits at the given place, and again, like the nth digit n minus 1th digit, right? And r is the radix or the base, whatever you are writing here, you keep it over here, and n is progressively either increasing or decreasing depending on whether you are at other side. If there is a number like this where 7392.21, then this can be written like exactly as follows, this one, but you have to add few more things over here. Those are 2 multiplied by 10 raised to minus 1 plus 1 multiplied by 10 raised to minus 2. So that will be the number, right? And that is how you can represent. And same is going to happen over here for any system. And so that is what written over here. It becomes minus 1, minus 2. So it is, this side is the decimal point. So both sides you have the possibility. One side you are multiplying and one side you are dividing actually, right? So that's the thing. Let's go with the number which you need to convert it to decimal. So therefore you have to follow the equation which is given over here using the general number system. Use that and you can have the decimal number. Let's look at that, how it goes. So if this is the number, this is the decimal point. So decimal point other side you are going to multiply with some minus number or you divide it, right? Whatever way you like it, both are synonym to each other. So you are starting from here. This is the 0th digit, this is first, this is second, and this is third, right? So you are going to multiply 1 with 5 raised to 0. This is the radix or the base. Base is 5, so you just add that. Another one, 2 multiplied by 5 raised to 1, and so on and so forth. So you can see same thing over here. And other side of the decimal point, you are going to multiply this with, this is minus first digit. So it's going to be multiplied with 5 raised to minus 1, and that is going to give you the equivalent decimal number, right? So here you can see that you will never see any number which is more than 5 or even 5. Okay, so you will never see that. Same is true for here. But both the systems are different systems. One is with base 5 and one is with base 10. Now let's look at another system which is we are going to convert it to 1 to 7.4 with the base of 8. So if you want to convert it, let's start from here. So it's plus 4 times 8 raised to minus 1, 7 times 8 raised to 0, 2 times 8 raised to 1, and 1 times 8 raised to 2. If you add all of them, you're going to get your number in decimal. So I am keeping this to you people to find it out. Let's look at the other system where it's a hexadecimal and which you want to convert it to decimal. So whenever you want to convert any system to decimal, you have to follow only and only one equation, which is an times r raised to n plus an minus 1 times r raised to n minus 1, so on and so forth, till you have to go till a0 times r raised to 0. If the system does not have anything after decimal point, if it is there, then you have to go with other side with a minus 1 times r raised to minus 1 plus a minus 2 r raised to minus 2, and so on and so forth till infinity, right? So depending on the numbers you can do that. So in this case, you know that hexadecimal is the one where the f is equal to 15, 5 is 5, 6 is 6, and b is 11, right? So all these are in hexadecimal. So how to get the decimal number from the hexadecimal? So you have to multiply each one of them with the appropriate digit or the position of the digit. So 15 times 16 raised to 0 plus 5 times 16 raised to 1 plus 6 times 16 raised to 2 plus 11 times 16 raised to 3. You just keep all these things, you will get the number in decimal just for you. The solution is already available, you use it. If in case other side is given, let's say point F, then you have to add 15 times 16 raised to minus 1. Okay, so whatever is coming, you just keep it over here. But note that both the calculations are happening separately. So the decimal points other side has to be added together and this side has to be added together, and that number should go here. So this will be in fraction and this will be in some integer value, right? Okay, so all well in that case. So now you are expert on converting any base, any number to decimal, or its synonymous with 10 base. If you want to do that, the easiest thing is you have to find out various digits and you have to apply this equation. So I'm writing two parts. One is, so this part will have a minus 1 times r raised to minus 1 plus a minus 2 multiplied by r raised to minus 2, so on and so forth, right? You can go till you have the decimal points, right? So you use that. So this is first part of the topic where you learn that to convert from one part to another part. But if you are interested in a other way around, you want to convert the decimal number to any system, so what to do? So in this case, if you remember, we used to multiply this side and this side we used to divide. This side actually it's multiply and this side it's divide. But if you want to go other way around, from decimal to any system, or let's say any base, let's call this base as m, or rather than this, let's call this one as radix, whatever radix are there, is there, from decimal to any radix. In that case, what you need to do is you have to divide this number with r, right? So that first number decimal is going to be divided by r. Whatever number is coming, it will have two parts. One is the integer and one is the fraction, right? So if fraction is there, in a case of, let's say if it is binary, if this is a binary system which you are interested, you are going to divide this with 2 and just look at the fraction. If it is other than 0, then you keep here that number as 1, and for the next round of division you are going to take this, let's call this one as I0. For the iteration 0, it's again going to be divided by 2, and you might have I1 plus some fraction. If this fraction is other than 0, you are going to keep it 1. If no, then if it is 0, then you keep it 0. So you will continue this till the time you are not getting the complete 0 at both sides. And if you one side means integer side, if you are getting 0, no problem, just fraction has to be available. When this is done, you might have some number, let's say b0, b1, b2, and let's call this one as bn. In this case, you have to follow from bottom to top. So whatever the number is there, you just place it over there, and that will be the equivalent binary number. Now let's assume that, so here we made it division. Understand the first part before decimal point. if it is this side with some fraction, decimal number, this side, then you have to multiply. If this is the thing, you have to multiply. So after point, if there is some decimal number, if you want to convert it to binary, after point, what you have to do? You have to multiply this decimal with multiply by 2. You will get some number, fraction. So note that you have to include this point here. Point times decimal multiply by 2 plus, sorry, you will have some integer part and some fraction part. So whatever with first iteration, you keep it here, I0 times 2, sorry, it's a mistake, let's say F0, the fraction time has to be multiplied with 2 and so on and so forth. You can find out some numbers. Each one of them is going to be given some value. That value is actually transferred from here. So note that this integer either it has to be logic 1 or logic 0, right? So those might be some, let's call it b minus 1, b minus 2, so on and so forth till b minus n. So it's all about going from top to bottom. So note that for the case of other side, it's going from top to bottom. In this side, it was going from bottom to top. So sometimes people are making mistake, but please do not make mistake. My students should not make mistake on such things, right? It's very simple. However, sometimes you make mistake in keeping the final number. So then don't do that. So let's go from here. If you understand the theory when you are converting from decimal to binary, but note that the procedure which I taught, it's true for any base, by the way. So if it is 8, then decimal has to be divided by 8. If it is 16, it has to be by 16. And same is true for here. Then it has to be multiplied with the given radix system, right? It has to be multiplied and this side has to be divided. So the crux of the story is as follows. If you want to convert any system to decimal, you have to follow this equation. And if you want to convert decimal to any system, you have to divide or multiply, right? So let's go with some of the example. If you want to convert your decimal number 41 to binary, what you are going to do? You are going to divide 41 with divide by 2. So what you are going to get? Two things. One is actually remainder and one is integer. So 20 plus 0.5, that will be the thing if this remainder is other than 0. As I told multiple times in the previous slides, if it is other than 0, then it will make the coefficient as 1, right? Same way, this 20 again will be divided by 2. Let's call this one as I0. So I0 got divided by 2 because of this binary system, by the way. Every time divided by 2 because of binary system. When you are doing this, it becomes 10 plus 0. Then again 10 is getting divided by 2. It gives you 5 plus 0. Again this 5 is divided by 2. That gives you 2.5, means 2 plus 0.5. This is other than 0. So it's going to give me the coefficient of 1. But in other cases it was 0. Again 2 will be divided by 2. It's going to give me 1 plus 0. Then 1 is going to be divided by 2. So this part becomes 0 and this part becomes 1 by 2. So note that when you are reaching at the point where integer or the quotient become 0, you have to stop here, right? So when you are stopping, and if you remember the technique which I told you, when you are converting a decimal to binary, you have to take bottom to top. So the equivalent number will be 101001 in binary for 41 in decimal, right? So this is what you're going to do it before decimal point. If it is 41 point, let's say 41.41, then you have to multiply this 0.41 multiply by 2, and you have to go with this, so it becomes 0.82, right? And you have to continue with this. 0.2 has to be multiplied by 2, and you have to continue with that, and you have to write down from bottom to top. We'll do some exercise on that also. So this is giving you some result, and totality you are getting this number with 1 2 3 4 5 6 6 bits are going to represent your number 41 in decimal, and you require 6 bits in binary. That is the meaning of that. Now let's look at that. So this is for quick revisit. That you have some integer 41. When you divide by 2, there are two parts. So I'm replacing this remainder with 0.5 with 1. If there is remainder, if it is present, let's call it logic 1. In the division with 20, it becomes 10, and there is no remainder. 10 divided with 2, it becomes 5, but there is no remainder. 5 divided by 2, there is integer as well as remainder, so that's going to be converted, and so on and so forth, so you can get the answer. So this is quick way. Same you can follow with 153. So 153, you have to divide with 8. That is going to give you, 19 plus 1, right? So that will be there, remainder. So that you have to keep it here. Again, 19 is divided by 8. So that gives you integer part as 2, because 8 2s are 16. So 3 is left, you keep it here. Note that here the numbers are coming less than 8 in the case of octal. So it will be from 0 to 7. Right? So that whole number you have to take. So if it is becoming 0, because 2 divided by 8 is going to give you only fraction, and that fraction is 2. 2 is coming directly from here to here, right? And there is no integer part. When integer part becomes 0, you have to stop here, stop, and you have to write the equivalent number from bottom to top. So it's 231. That's in octal system, right? Same thing you can follow. If it is 153 point some numbers are there, so you have to multiply that. You don't have to divide it, but you have to multiply it. Now let's assume that there is a decimal system 0.6875, because this is what you might want to learn, because you learn it this side but you haven't learned this side. I gave one general explanation, however we need to learn it through one example. So in that case, 0.6875 in decimal, you need to convert it to binary. You need to multiply that number with binary, means 2. So multiply by 2. Write down something. You might have some integer part and some fraction part. Definitely we will have some integer 1, and rest of the part is coming here. Let's call it f0. F0 again will be multiplied by 2, some integer part and some fraction part, right? So you just keep on looking into that and discard all these fractions. You go from top to bottom, and these integers will be either 0 or 1. That combination is going to give you the equivalent binary number. Let's look into that. So if it is 6875, in like 0.6875 multiplied by 2 is going to give you integer 1 plus 0.3750. So it's 1.3750. That's the multiplication number. So you kept it in two different things. So 1 plus 0.3750. You are going to multiply 0.3750 with 2. So that's going to give you 0.750. It does not have any integer. So it's placed as 0. 0 plus 0.750. This is again going to be multiplied by 2. That's going to give me 1.5. So 1 plus 0.5 with 000. This 0.5 will be multiplied by 2, so that's going to give me 1.00. So when you reach 0, you can stop here, and you have to make sure that you are looking at these integers from top to bottom, as it is available after decimal point. So that makes, and you have to just dump this fraction somewhere, there is no problem. You are interested in this number, so 1011 after decimal. So that's the answer for your binary. So you can write it down 0. So now if it is some number called 0.513 in decimal to octal, octal is 8, so you have to multiply by 8. But if it is this side, let's say 1.513, then to convert this 1 to octal, you have to divide 1 by 8, right? So decimal points this side, you have to divide, and decimal points this side, you have to multiply. It's opposite of the one which you studied from any system to decimal, where decimal points other side you have to multiply, and decimal points right side you have to divide. So in this case, it's the reverse of that, right? So 0.513 you have to multiply with 8 constantly. So what you are going to get is 4.105. Then 4.105 is fraction part. You have to only take the fraction part. So 0.105 multiplied by 8, that's going to give you 0.832. 0.832 again multiplied by 8, it's going to give you 6.656, and so on and so forth. As this is fraction part, it depending on how many number of bits you have available, you can write down this code, right? So still, look, as this is a fraction, it depends whether it's going to give you the round of number or not, but there is no possibility sometimes. So it's keep on going. Maybe it can go till 20 such iteration, but still you will not get the round of number. Then it depending on how many bits do you have in the particular system, so that you need to find out. So if assume that I'm saying octal number, I want it till 3 4 like 6 decimal points only, right? So you can write down 6 decimal point. By the way, 7 decimal point is also possible. However, we are not going to do that, or that's enough, I think. So then we will stop it, right? So you as an engineer need to ask how many number of bits do you have. Then you can give the proper answer, right? So that's an assumption also. So sometimes if I am giving you a question that convert this to an octal number, then you have to write your assumption that I have only 6 bits are available after decimal point. That's why I am using with 6. You might also say that I have only 2 bits, so I am stopping here at only with 0.40 only, right? So depending on the number of bits, you can have the answer. So in this case, just discard all the numbers after decimal point, and you have to start from top to bottom. Whatever is available, you can write it down that, right? So you can write it down that, and that will be the equivalent octal number. So octal number is 0.406517 in octal for the case of 0.513 in decimal. So now one more important thing is octal and hex. Although we studied different systems like with base 3, 5, many fancy stuff we studied, but we are mainly interested in 3 systems: binary, octal, and hex. Right? For any computer hardware, we only need these 3 systems, right? And of course, decimal is very much important because we studied everything in decimal. We have to convert it from there. However, other systems are actually not so much useful for digital logic, or in the case of computer organization, at least at this moment. Maybe you as an engineer, in future you can invent something where such base systems might be useful, but we will restrict ourselves to that one, and we are not learning how to go from you know from like base 5 to base 8, base 5 to base 16, or something like that. So intermediate, and that's why like we did all the examples with decimal to any system and any system to decimal. Decimal we kept it in between. So in case if you want to do that, then of course you can convert it to decimal, and you can further record it for the given number system. But other like from one system to another system also possible to make it workable the way we did it, but you need to work on its algorithm, that how it uh, can be converted. So right now there is no trick I am teaching, but there are possible. So we are not going into that, or we are restricting because of the only reason that we are interested in binary, octal, and hex system, and our mother tongue is decimal, and we want to convert it to other language of computer, which is binary, octal, and hex. That's why we learn between binary to we learn between decimal to binary, octal, hex, or binary, octal, hex to decimal. We learn that. And at the same time, you might have the question that I want to convert to binary to octal, or octal to binary, and same for binary to hex, or hex to binary. So in that case, it's very simple and it's very easy going. We know that 2 raised to 3 equal to 8. So this 8 is the combination possible with 3 bits. And 2 raised to 4 makes 16, means x is possible with 4 bits. So all binary system which is of combination of, let's say, 3 bits, it can create octal. If it is combination of 4 bits, it can create hexadecimal. Let's look into that, what I mean to say. So let's assume that there is a number which is like this, that 10110 001 101 011 dot 1 111 100 000 110. So to convert that to octal, just you have to make sure that starting from decimal points other side, you have to start, means this side and this side. So make the combination from this one to the least significant bit to the most significant bit in a combination of 3. So here nothing else is available, so you make it with only with 2 numbers. In this case, with the combination of 3, you can make this, and each one of them is going to represent some number in that system. So note that it will never exceed 7, because you are only combining 3 bits. So 3 bits can give you at the most 7, or it's between 0 to 7. So 8 will be there, so it will never exceed. So in this case, when you are going to write down its equivalent number, it's very simple. It's 26153.7406 in octal. Same way, if you are interested in, let's say, hex, you're going to make the combination with 4 numbers. Like this, right? So this makes 1011. So that's 3 plus 8, 11, right? So 11 in hexadecimal, just for your information, 0 to 9. Then A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. So that makes 3 plus 8 makes 11, and 11 is B. So you keep here B number. Here for the case of 0, 1, 0, 1, 0, 1, 0, that makes 2 plus 4, 6. So 6 is here. In this case, it makes 8 plus 4, 12. So that's C. So 1, 0 makes 2. And with decimal, we're going to make all 1, it's F. All 0, 0. This is 0, 1, 1, 0. That makes 2 plus 4, 6. So that number in hexadecimal. Right? So all are equivalent to each other. So this is very easy, and same way you can go in a reverse way also. If you want to convert this to, let's say, binary, it's very easy. Just you keep the its equivalent 4-digit number or 4 bits of number, and then you are done. There's no problem in that, right? So you can convert the octal to hex, or hex to octal, and all these things you can do it. So those some of the example have been kept over here. So thank you very much for today. We'll study further in the next lecture. Thank you very much.